In our last graphical example, example 2D, our system is x equals 4 and negative x plus 3y is equal to 6. Okay, so we're going to again solve this by the graphical method. All right, so our first equation is x equals 4. Okay, notice there is no y. Okay, so this, it doesn't have a y. And think back to what we talked about when we discussed graphing lines. If you have something of the format x equals a number, okay, that means it's going to be a vertical line through that point. Okay, so basically, since we have x equals a number, okay, this is going to be a vertical line. So let me just write this down. So x equals 4. Okay, this is a vertical line. Okay, and the way we graph it, okay, is since it says x equals, you're going to go to the x-axis and you're going to find where x equals 4. So that's right here. Okay, and it's going to be a vertical line through this point. Okay, so vertical means up and down. All right, so let me draw my line in. Okay, so there we go. Okay, so this is the line x equals 4. Okay, and now I will go and graph the other line. Okay, all right, so the other line, or the other equation, is negative x plus 3y equals 6. Okay, we can definitely put that in y equals mx plus b form, so let's go ahead and do that. All right, so we need to isolate this 3y, so we're going to add x to both sides, and we're going to get 3y is equal to x plus 6, and then I'll go ahead and divide everything by 3. So we're going to get y equals, okay, so this is, if you're dividing by 3, it's the same thing as multiplying by 1/3. Okay, so 1/3 x plus, okay, 6 divided by 3 is 2. Okay, so there you go. So for this line, now that it's in y equals mx plus b form, we can identify the slope and the y-intercept. The slope is the number in front of x, so it's 1/3, and the y-intercept is 2. Okay, so let's go ahead and plot it. We'll first put down our y-intercept of 2, okay, and now we will apply the slope of 1/3. Okay, so top number is your rise, bottom number is your run. Okay, they're both positive. Okay, so we're going to go up 1, right 3. Okay, so we'll go up 1, right 3. Okay, and we'll just keep repeating that process. All right, so that's enough because we can already see that there's going to be an intersection point. Okay, so here we go. So here's my line. Okay, and I'll go ahead and label this one. All right, so this is the negative x plus 3y equals 6. Okay, so obviously there is an intersection point. Okay, right here. Here's the intersection point. Okay, because if you're solving by the graphical method, you've got to graph each line out and then look for the intersection point. So from this example, you can kind of see the drawback of doing the graphical method. This particular intersection point doesn't land nicely on a grid point. Okay, so there's going to be a decimal involved, at least for the y coordinate. Okay, so you can try to estimate it, but maybe, who knows if you're right or not. Okay, so that is a drawback, and you can read this down here. It says, notice from this example D that the graphical method does not always yield an exact solution, meaning you don't always land on a nice grid point. Okay, in this situation, it's better to use one of the other methods that we are going to discuss, either substitution or elimination, to solve the system so you can get a completely accurate answer. Okay, so we're going to start talking about substitution here. Okay, you can kind of eyeball this answer. You definitely know that the x-coordinate's going to be 4, okay, for sure. The y-coordinate looks like it might be 3.5, but who's to say for certain, okay? So what you can do, the easiest thing to do here would be to do the substitution method, okay? Basically what that involves, and we're going to talk more about it, but basically what it is you take one of the equations and you solve for one of the variables, and then you substitute that result into the other equation, okay? So it's actually pretty easy here because the first equation is already solved for one of the variables. You know x has to be 4, okay? So what you would do, and I'll do it, I guess, over here to the side. You know that already that x equals 4. So then you can come to the second equation, which also has to be true. So write it down and then use the fact that x has to be 4. So I would have negative, and then wherever I see x, I'm going to put in a 4 because x has to be 4 because of the first equation. So plus 3y is equal to 6. Okay, and notice you are left with an equation that only contains a y. Okay, so you can solve for the y coordinate. Okay, so we'll add 4 to both sides. We'll get 3y is equal to 10. Okay, divide both sides by 3. Okay, so the y coordinate was actually 10/3. So that's 3 1/3. Okay, so it wasn't 3 1/2. Okay, so the actual solution to this system is the x coordinate is 4, the y coordinate is 10/3. Okay, and again, that probably was very difficult to read off the picture. So you need a more rigorous method like substitution or elimination to determine that decimal. Okay. All right. So I think now we are going to go ahead and explore substitution. Okay. Before we do that, okay, I want to mention something, and this is very important for solving systems of equations in general. Okay. If we look through these 4 graphical examples that we just did, okay, so I'm going to go back to part A. Part A, we got exactly one solution. There was one intersection point. In part B, there was no solution because the lines were parallel. In part C, we got infinitely many solutions. Okay, and then again in part D, there was one solution because there's a single intersection point. Okay, these examples summarize what happens when you're solving a system of linear equations, whether it's a small system like this where you have 2 equations and 2 variables, or you have a bigger system. Okay, these are the possibilities. These are the only possibilities. You're either going to get exactly one solution, no solution, or infinitely many solutions. Okay, there will never be a time that your 2 lines intersect 2 times only or 3 times only. It's either going to be once, infinitely many, meaning they're the same line, or they're never going to intersect. They're going to be parallel, so there's no solution in that case. Okay, so before we go on into substitution and elimination, I just want to touch upon the terminology you might hear associated with the number of solutions to a system of equations. Okay, so again, this is just some vocabulary you might hear, and again, right now we are studying 2 equations and 2 variables, but again, this terminology will apply as the number of equations and number of variables expands. Okay. Again, what I have on page 5 is a little box, and it's representing every time you solve a system of equations. These are the possibilities. Either you're going to have your lines are going to intersect once, or not at all, or they will be the same line. So this is representing when you have 2 lines and they intersect once, this is going to be one single solution. Okay, and then the next one, you have 2 parallel lines, so they will never intersect, so that will represent no solution. And then lastly, you know, think about red and blue make purple, so the lines are on top of each other, so they are the same line, so this is going to be infinitely many solutions. Okay, those are your only possibilities when you're solving a system of equations or system of linear equations. Okay, so again, there's some terminology you might hear, so let's go ahead and go over that. First bullet point there, it says a system of linear equations is consistent if it has one or more solutions and is inconsistent if no solutions exist. Okay, so consistent means it has a solution, inconsistent means no solution. Okay, all right, and then there's the terms independent and dependent. Okay, a consistent system is said to be independent if it has exactly one solution and dependent if it has more than one solution. Okay, so independent means it has exactly one solution, and dependent means it has more than one solution. Notice to use the terms independent and dependent, the system has to be consistent. It has to have a solution, okay? All right, so let's go ahead and look at our 3 different possibilities for solving a system. We're going to label each situation as consistent or inconsistent, and then also independent or dependent, okay? All right, so in the case of one solution, there is a solution. So this would be a consistent system. And then there is exactly one solution. Exactly one solution means it's independent, okay? So if you were dealing with the case of one solution, that is a consistent system and it's independent, okay? All right, so next, if you're dealing with 2 lines that are parallel, there is no solution, okay? No solution means it is inconsistent. Inconsistent means no solutions exist, okay? So we would write, this would be an inconsistent system. And then in this case, because there's no solution, we cannot apply the terminology dependent or independent, okay? Because to apply these terms, it has to have a solution, okay? All right, so then in the case of infinitely many solutions, remember there is a solution, there's just tons of them, okay? So this would be a consistent solution, or sorry, consistent system because there is a solution, okay? And then since there's more than one solution, this would be a dependent system, okay? So if you hear this terminology, this is what it means, okay? So this is a great summary of the possibilities for how many solutions you can achieve for a system of linear equations, okay? And also the terminology that goes with each situation. All right, so now we will get into the substitution method.